All right, cool. Okay, welcome to lecture 13. Today we're talking about regular expressions, which are a pretty cool thing that have a lot of both theoretical and practical applications. So what we're going to talk about here is that regular expressions are kind of a nice use case for functional programming and a really important thing in computer science. This might be one of the most practical things you learn. Okay, so all right, we're going to talk first about this problem of text validation. And the idea is that we want to validate user input. This is something that happens all the time. You read input from a user. You want to make sure that it's not dangerous, because you might get an input, put it into your database, and then run that, and then later find out that someone gave you input that was specifically made to crash your system. So we want to stop that from happening. So we want to validate it. In particular, let's think about as if we want to find usernames or email addresses rather. And the structure of an email address is going to look like this. It'll be name, append, or at website, the name of the website, and then dot and extension, okay? And that's the structure of an email. And we want to take that and then make a function called validate email that takes in a string and tells us whether or not it adheres to this specification, if it's a valid email address, okay? And this is dependent on a few things, which is we need to know what a valid name, website, and extension are. So I'm going to give the specification for that now. But let's assume that a name, or rather an extension, can only be org or com. Okay, so our email addresses can only end with .org or .com. Furthermore, assume that a website has to be only alphanumeric characters. That is, all of the alphabetic characters and all of the numerical characters. And then assume that a name has the same condition. It needs to be fully alphanumeric, plus underscores and plus periods. Okay, so they're kind of similar, but not exactly the same. To fully implement this function, we're going to define some functions called consumer functions. Okay, and the idea behind consumer functions is if you give me an email, like if you give me my work email, then I want to I want to turn this string into a character list, and I want to pop off characters that match my thing I'm trying to validate, that thing I'm trying to consume. So if I'm trying to consume names, well, names can be any sequence of alphanumeric characters. So I would take off all of the B-R-A-N-D-O-N, until I get to this append, at which point I would say, oh, that's not a name, so I'd stop. So we're going to define a function that does that. Okay? So we're going to have two functions called consume name and consume website. Consume name is going to evaluate to the suffix. That is, like, if I have my entire character list, I can put a line in the middle, and this is my suffix that satisfies this. My suffix is anything that's not part of a name. I take off the prefix. I take off characters until they no longer satisfy the name. And then for consume website, I just take off characters that match the website. Okay? And I'm not going to write it on the board for you, but here's how we can implement it. If I have consume name, I check. It's a recursive function. If it's empty, I can't take anything off, so I return the empty list. If it's C-cons Cs, if the C is alphanumeric, I take it off and I continue to consume on the suffix. Otherwise, if C is either dot or underscore, I also do the same thing. I take it off and I consume. Otherwise, if it's none of those things, well, like if it's append, if it's at, then I stop in my tracks and I leave the whole thing because I can't consume anymore. Okay? So once I've done that, I'm done. And then for consume website, it's the exact same, but now we don't allow dot or underscore. Okay? So all we do is we consume all of the alphanumeric characters from the front until we see something separate. Okay? That's all we're doing. Finally, we're going to write our validate email function. And I'm not going to write it out again, but here's what it's doing. Recall the string.explode function that takes a string and turns it into a character list. So I take my string, I turn it into a character list, and I consume all of the characters that could be a name from the front. So I take off B-R-A-N-D-O-N, and I'm left with this. And I case on that. If I have at and something else, well, I take the at off and I get C's, and then I consume website on it. So I take this off, and then I take off S-E-M-G-R-E-P until I see a dot, at which point I say, well, okay, I'm done. Do I have .org on the front of what's left, or do I have .com? Well, this is .com, so we just pattern match on the first 4 characters of my character list that remains, and then I get true. And if any of those conditions were false, then validate email fails because it doesn't look like an email. Okay? And that's how we validate an email. Except there's a little bit of a problem here. Okay? This is not quite right. There's a bug because what if I put a bunch of random nonsense at the end? Like I said, .com ASDF. Well, this is not a valid email according to our specification, but this is not a valid email, but it will pattern match to this, right? We will get that this will match because the end is just a wildcard. We want to make sure that we end with .org or .com. So we're going to make it just the list of .org and .com. After we do that, now we're done. This is how we validate an email via this process of taking things off the front. Okay? So we make sure the extension is the last thing. Well, okay. This is what we call a hand-rolled function, as in I had to manually write this validate email function for you. And while you're like relatively sure it works, we still had a bug. We had a bug we didn't know about, right? So what we want to do is we want to avoid that because this is tedious to write. It was really manually constructed and it wasn't easy to do. Or rather, it was easy to do, but it was easy to get wrong. So we don't want that to happen. If we ever write code, we have a potential for problems. So the idea, our mantra is more code, more problems. So let's try to have less code, okay? And this model might be similar because we might be interested in a bunch of problems that look like this. Suppose we're interested in phone numbers. That's like something, three things, and then four things, or three things and then four things again, right? So like this is a kind of a similar problem where we need to consume input. But every one of these functions we write, it's ugly, it's tedious, and it sucks to do. So let's not do it. Okay, let's try to automate this process. So what we're going to do, is we're going to write a function that takes in some type and then produces to us one of these validation functions. We're going to try and encode this validation problem in a value of some type. And that type will be called the type of regular expressions. Okay? So we're looking for like the essence of a string validation problem, and we're going to turn it into something called a regex. Okay? So part 2, this is where I tell you about what regular expressions are. I always like to think about it in terms of these two XKCDs. The idea is there's this one where basically these two people need to look through 200 MB of emails to find something that looks like an address. And then Randall Munroe swings in on a Tarzan swing and then says he knows regular expressions and he solves it. And that's perfectly fine. That's kind of what you'll be able to do sort of after this lecture. And the second thing is also a similar one where this guy's got 99 problems, so he uses regular expressions, and then now he has 100 problems. It's easy to use regular expressions wrong, but thankfully we're not going to be using regular expressions. We're going to be learning about how they work. Okay? So PCRE stands for Perl Compatible Regular Expressions. It's an old library for regular expressions and a syntax for regular expressions. And we're going to take that and we're going to drop the PC because we don't have time for it. We're just interested in the regular expressions. We're going to learn about the theory behind it, which means that basically after this lecture, you're not going to know how to write regular expressions. You're not going to know how to use them, but you will know how they work. And that's the most important part, okay? So that's the idea of this lecture, okay? Here's the idea. What makes up a validator? What is a validator? To be a validator for a particular thing, I want to be able to do a few things. In particular, I should be able to concatenate two things I'm looking for together. Like how I say I want a name and then I want an append. That's called concatenation. I want to be able to do one thing and then put that next to another. Alternation, which means I want one of two things. I want to be able to match either .org or .com. Both of those one of those needs to be true. I don't care which. So one of either. And then finally, iteration. I should be able to match a pattern, but as much as I possibly can, because I need to match a website, for instance, I needed to be able to match an alphanumeric character any number of times. So we iterated, basically. We said, give me an alphanumeric character and consume an alphanumeric character any number of times. Okay? So these three things are going to boil down the essence of what we want in a validator. And this should seem like a recursive definition because it is. Okay? So let's describe what the mathematical definition of a regular expression is. And here's the idea. We're going to introduce a few key ideas, but central to it is going to be this thing. We're going to have alphabets. An alphabet is of type car list. It's a set of characters. We notate it capital sigma. And capital sigma might be A comma B, for instance. Okay? And this is just the alphabet of characters that we're interested in strings over. And we're going to have strings, which are of type string in SML, okay? So a string over this particular alphabet might be A, it might be A, B, B, A, it might be B, B, B. These are all valid strings. We also have the empty string, which is possible. So we can't really draw that, so we notate it epsilon, okay? And these strings also need to be finite in length, okay? We're only interested in finite length strings. Furthermore, let's introduce a concept called sigma star. If I have an alphabet sigma, and I take the star of it, this is of type string list. And this is equal to all strings over sigma. So if I wanted to take the star of the alphabet A comma B, which is our toy alphabet of choice for today, I would get that this language, this sigma star is going to be the set of firstly the empty string, and then A, and then B, and then AA, and then AB, and then BA, and then BB, and so on and so forth. It'll be every finite length string that could be composed of A and B, which includes the empty string. That's what we call sigma star, okay? And finally, we have a notion of languages. A language is also of type string list, but a language is a particular subset, a collection of these things that we're interested in. So L is a subset of sigma star. And what I mean by that is we can highlight a certain number of these things in sigma star that we're interested in. And these form a language. So our language might be epsilon, and then B, and then AB, and BB, and nothing else. But this is a subset of all possible strings. A language is just the strings over the alphabet in particular we're concerned with that we're interested in. Only these strings are we interested in, okay? This is a lot of basis in like formal language theory and computability, theoretical computer science. But the point of having this is just that we're saying that certain strings we're interested in. We want a validator that says true only if it's a string in the language. So a particular, one example of a language we might be interested in, and ignore this for a second. One example of a language we might be interested in the context of our email matching problem, we might be interested in L, well, where L is equal to all email addresses. This is a valid language. And it's a language because the string ABA is not in this language because it's not a valid email. So when we talk about validators, and let me move forward a bit here. When we talk about validators, we're interested in a function f that checks for membership within the language. So a function f from string to bool is a validator if it returns true only if and only if the input it gets is in the language. And otherwise it returns false. We usually require that these functions are total, okay? It turns out that via this specification, regular expressions are what lets us kind of achieve these validators. It's what lets us implement them very neatly and very compactly, succinctly, okay? We can't match every language using regular expressions, but in practice, a lot of them we can, okay? That's the point of this. So let's define the structure of a regular expression. So if I have the structure of a regular expression, it's just going to be these things, okay? And I'm going to give you the mathematical notation, but it's not going to matter super much here. It'll look like math, but this is just notation, okay? We say a regular expression R is one of 6 things. It is 0, which is a symbol. It's not math. It's not 0, the number. It's just a symbol. It's a special regular expression 1 or 0. We also have the regular expression 1. We also have the regular expression C, where C, well, rather for any C that's in our alphabet. Okay? And then finally, where R1 and R2 are regular expressions themselves, we have the regular expression R1 plus R2. And again, these look like math, but I'm going to give you the meaning in a second here. I'm just going to define the syntax to you right now. Okay? R1 plus R2 is 1. Then R1, R2, which is the concatenation, or rather the juxtaposition of R1 and R2. We just put them next to each other. And finally, R star, which is called the Kleene closure, or the Kleene star, rather. The Kleene star of R. Okay? So we call it R star. And this is just the syntax of a regular expression. These are the 6 things that a regular expression can be. And note that it's recursive because a regular expression might be composed of other regular expressions. If this looks to you like a data type declaration, that's because soon we're going to define it as such. Okay? If you think in code, this should help. Okay? And then the language of the regular expression C is the language that has just the string C in it, right? Because there can be a string that has exactly 1 character in it. So it's going to be this. Remember, strings can be any length, but it can also in particular be length 1. Okay? So this will be fn. Well, this is harder to phrase. In SML, we're going to say like quotation marks C. But this would actually no. This is perfectly fine to say. What am I talking about? Okay. Like as in the singleton string of containing just C. So like if for instance, if this was literally L of C, the character C, this would literally be the lambda that you write to validate this language. It would take in the singleton string C. Is there a question? Yeah. What's that? Empty string? No. This is just C. That's the regular expression. And then R1 plus R2 is going to be R if R is in L of, or sorry, S. If S is in L of R1 or S is in L of R2. I'm not going to write a lambda for this one. Okay? So R1 plus R2 means it can come from either regular expression. What does that sound like? Alternation. If I have one of 2 regular expressions I want to match, I might have one regular expression for .org. I might have one regular expression for .com. If I plus them together, now I have a regular expression for my extensions. Okay? And then you might have a guess for what these last 2 things are based on that. R1, R2 is going to look the same, actually. It's going to be S1, S2 for S1 in L of R1, and S2 in L of R2. And when I write S1, S2, I mean the concatenation of 2 strings. Like I could write string concat 2 here, like S1 append S2, right? Or caret. But this is what it means. It just means take 2 strings from either language and shove them together. All right. So for instance, if I wanted to do this, I might do this for my append regular expression and my name regular expression. And I would get one regular expression that's the name and the append. Okay? And then finally, this one's a little harder to describe, but it's going to look like this. Let me think of the right quantification here. S1, S2, ... Sn, where for all I less than or equal to n, whoops, S of I is in L of R, n greater than or equal to 0. So what R star means is I take a string in R star, any string in R star, any number of those strings, and I shove them together. I put them together. That means I repeat a string in R star any number of times. It doesn't need to be the same string. Okay? So that means that if I wanted, for instance, literally, actually, we'll look at some examples in a second, okay? But the point is that I'm going to take some strings in R and then repeat them any number of times. And I might do it 0 times in particular. So that means the empty string is always in this language. It's okay if you don't get the finer points right now. That's kind of like a harder thing to remember. All right. Oh, yeah, I can also just write that. But yeah, whatever. Yeah, another way to write this is that this is just the union of their languages. Okay. Okay. Any questions on this? This is just a mathematical definition. We'll go through some examples right now. Okay. Oh, yeah, and then in English, please. So L of C is only C. L of 0 is nothing. L of 1 is only the empty string. L of R1 plus R2 is anything matched by either of my sub-regular expressions. L of R1 and R2 is any string, S, that can be split into two parts, a prefix and a suffix, such that the prefix comes from R1 and the suffix comes from R2. Okay? That's what it means. Any string that looks like this. And then LR star means any string that's something matched by R, but 0 or more times. We also called it the Claney closure, after Stephen Claney. Stephen Dole Claney? He was a lieutenant commander in the US Navy, I learned. So he came first, and now we are here to study him. So this is regular expressions, okay? Now we're going to look at some examples. All right. So in this case, suppose that we're interested in just the alphabet A comma B. If I have the regular expression A plus B, remember we can do that because A and B are both regular expressions. My language is going to be literally just A and B, right? If I have A, B, A, A, where, A, B, A, A means concatenated a bunch of times regular expressions, plus B, A, A, my language is, again, just those two things, okay? If I have A, B, A, A plus B, A, A, the previous thing, and then that whole thing parenthesized and then concatenated with B, then I get everything in the previous language, but also it has a B at the end. It has to have a B at the end. That means that A, B, A, A no longer appears in this language, okay? If I have 0 plus A, I get A. If I have 1 plus A, I get epsilon and A. And then if I have A star, that means epsilon, A. Every string that might be something in this language 1 or more times, or 0 or more times. Yeah. Was there a question? Everything to the left and right of a plus is a regular expression. In fact, every fundamental unit here, except for the parentheses, are themselves regular expressions. Okay, that means that A is a regular expression. B is a regular expression in here. BA in the middle here is also a regular expression. We're just putting them together. Yeah. We're jamming them together. No, because this is concatenation. When you concat something, you take something and you transform it into something else. That means that, for instance, if I had A, L of A, do you agree with this? Yeah. Then, if I take this language and I put a B at the end, I take everything in here and I put a B at the end. So, for instance, if I had no pluses, if I had no pluses and no stars involved, it would just be everything in there. Okay? All right. These are the examples, so you're supposed to understand now, hopefully. So if you don't, any questions? Or I can do a more involved example if you'd like. Yeah. Yes, of course. Okay. AB star, that's a good one. AB paren star or A paren B star? Like this or this? These are two different regular expressions. Actually, let's do both. Let me illustrate the difference here, because that'll help. Okay, so these two regular expressions I claim to you are different. Here's why. AB star means, okay, so first of all, what is the language of AB? Just AB. I just answered it for you. The language of AB is just the string AB, right? So that means that the language of this thing starred means I take anything in that language, that is AB, and I repeat it 0 or more times. So the 0 case is epsilon, the empty string, right? The 1 case is AB. But my question to you is then, can I put ABA in this language? Well, AB is in the language, but A is not. So this is not something in there 0 or more times. So in fact, ABA is not in this language. It'll be ABAB. And then ABABAB. It'll be finite repetitions of the string AB, okay? So it will always be even in length, okay? All right, is that clear? But this one down here is different. So what is the string in the language of A? It's A, the string A. But what's the language of B star? The language of B star is going to be anything in B repeated 0 or more times. So let me make it very explicit. L of A is equal to the set A, L of B star is equal to epsilon, if I repeat B 0 times, and then 1 time, and then 2 times, and then 3 times, so on and so forth. So if I concat these together, I take every string in here, and I put A in front of it. So my result is going to be A, B, or sorry, A, B, A, B, B, A, B, 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 dot, dot, dot. Yes? The full sigma star over, yes, over A and B. Yes. Yeah. I will move on from this shortly because this stuff doesn't matter super much, but yeah, this is that's a good question. So, oh, and also, whoa, oh my God, how did they get over there? What? Okay, I'll give you one of these. Cool. Yeah. You said 0. Who said that? 0 what?
0 A and 1 A.
Yes. So in this case, what we do is we take every string in here and we concatenate it to every string in here. But how many strings are in here?
Oh,
0. So this is going to be the empty string. Sorry, it's empty. But this is A. And now we've come across why they're called plus and times, because 0 is the multiplicative killer, right? And then 1 is the multiplicative identity. And then 0 is the additive identity and so forth. It doesn't really matter. There's a cool midterm review problem I made about this at one point. I don't know if we're still running it. But yes, this is examples, okay? If everyone gets kind of what's going on here, we're going to move on. Just to get flavor of intuition for, yes. Language for A, B star. A, which one? The, yeah, this one. So yes, this language is A, B repeated any number of times. Oh yes, the language for the sub-regular expression here is just A, B. For this,
yeah.
That would be this, actually.
Okay.
Yep. Yeah, so as a recursive definition, we rely on what the language of the thing immediately prior is. Okay. Yep, good question. Cool. That was good enough. Okay, let's move on. These are, I realize you've had enough fun of hearing me say A, B, A, B, B, B over and over again, but we're going to move on from that. Hopefully it'll get better. All right, I just stuffed a bunch of math in your brains. Why are we here? What's going on? What are we doing this for? Okay. The reason why we're doing this is because this formalism here is going to be a very useful thing for really specifying any language that almost every language we're interested in, okay? These regular expressions are composable. That means that if I have a regular expression I'm interested in, I can just take it and shove something in front of it, and now I have a new regular expression that does something moderately similar, okay? And composability is really cool, because now I can upgrade my email regexes to emails that maybe have like an HTTPS at the front, so on and so forth, right? So this is going to be really useful for reuse and for kind of just conceptually understanding what these do. So if I wanted to write a regular expression for the email thing I was talking about, let r sub an be the regular expression that matches all alphanumeric characters. You could write it as a plus b plus dot 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 plus z plus 1 plus 2 plus dot 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 plus 0. Okay, you can literally manually write it out that way. Then an email would be alphanumeric character plus dot plus underscore. And remember that plus means or here. So alphanumeric or plus, or sorry, or dot or underscore. And that any number of times. Hence I have my Kleene closure here, my star. Okay? And then I must see an append, so I can cat it. And then I must see an alphanumeric character any number of times again. Then I must see a dot. And then I can see either org or com. Okay? This, and worth noting, this definition also permits empty names and emails, but it's whatever. It would be a lot of pain to rectify that. Okay? You would just repeat it and then put it to the left of it. Yeah. Except without the star. Yeah. Does everyone see why this is a regular expression for the email example I gave at the beginning of lecture? Just any number of these characters, append any number of these characters, and then .org or .com. Okay? Okay. Okay, I think we're going to move on then. Oh, shoot, that was not the end. Okay. Another interesting fact is that we can use regular expressions with these things called finite state machines. And I'm going to skip over all of this, but basically, if I have a regular expression AB plus BA, I can represent it with a graph like this. It's a machine that reads input. Basically means that you start here, and if I read an A, I go to here. And then if I read a B, I go to here. And then this circle around here means it's an accepting state. It means that if I ever end up here and I'm out of input, I'm good, I'm done, okay? And correspondingly, if I'm in the starting state and I read B, and then I read A, I'm in the accepting state, okay? This is just a way of reading some input and then trying to see whether or not it's accepted. And there's a correspondence here where you can always find one of these DFAs, we call them, for any regular expression, okay? Okay. So I'm just going to run you through the example real fast, which is that if I wanted to put AB into this, I start here, and my remaining input is just the string AB. I haven't read anything yet. I just started. Then I give it A, so I go here, and now I have B left. Now I read B, so I go here, and I'm out of input. So now I end up here. This is my final destination, so I accept. That means that AB is in the string of this machine guy. If I had given it ABA, that means that I would have done A, B, and if there are no arrows, it means that you fall off the edge of the world. You fall off the map, and it means you die, okay? So if I gave it ABA, I would have nowhere to go. I fall off the map and I die, and then I don't accept. Fair enough? But for brevity, we usually don't write that. Okay, so this is a automaton that accepts literally only just ABA, or sorry, AB and BA. And A itself, if I just gave it A, that is if I ended up here, this would not be accepting because it's not circled. Okay? All right. This is just to give you some intuition, and then hopefully if you get that intuition, I'm going to tell you that this is a regular expression, a automaton for this regular expression, meaning that any number of A's, because if I read an A, I go back. So I go A. And then precisely 2 B's, and then any number of A's. So the things in this language might be like, I don't have enough space to write it down. But basically, this would accept any string that's A's, and then 2 B's in the middle. And that's it. Okay? And you can read over this on your own, but I'm going to let you go to the quiz. All right. Get up. Okay. We're going to move on to implementing this. I gave you all the math. We're going to put it in code. I promise you, 10 to 12 lines, generous white space. Okay? It's going to be pretty simple. All right? But all this notation, all this like mathematical stuff is just to cement your understanding of what the hell the code is actually doing. Okay? So now we're going to talk about matching regular expressions. So we saw that like if we have this DFA, we can kind of already match it. If we have the DFA, we just like go through the DFA and then until we reach or we run out of input. It turns out it's actually pretty involved to produce a DFA from a regular expression. But that is what people do. We're not going to go that route. Instead, what we're going to do is we're going to straight up decompose on the regular expression. Sorry, the other thing I wanted to say to you is there's this guy called Russ Cox. I think he works at Google. Basically, he implemented Google's RE2 library, which is like one of the best, like most standard regular expression libraries out there. And he kind of commented this thing I thought was super great about how like regular expressions are like where theory meets practice. It's one of the best examples of where good theory leads to good practice. Everything I told you about this theory is what they actually do. It's what actually happens. Because this theory, if not for it, people would be solving regular expressions in a really dumb way. That goes from 900 milliseconds to 90 microseconds, I believe the figure was, in terms of matching length. Okay? Blech. So that's kind of my motivation for you here, which is that like good theory, good practice. Programmatic thinking is mathematical thinking. Okay? So let's get into it. We are interested in this data type, which I will write up for you in SML. Okay? I gave it to you in terms of math, but now we're going to do it in SML. Okay? So if I have a regular expression, it's either 0, or it's 1, or it's a constructor car given an actual SML character. Okay? Or it's going to be plus of 2 regular expressions, which means a tuple of those 2 regular expressions. Or it's times, which means like concatenation of, again, 2 regular expressions. Or it's going to be the Planey closure. It's going to be the star of a single regular expression. Okay? So, that is all you need to know to do regular expressions, okay? It's these 6 variants. And we're going to define a recursive function that goes over all 6 of these variants and then matches whatever language we want. Okay? And I realize, it looks scary. You already saw it. But this is it turns out that regular expression matching is an extremely good use case for CPS. And I'm telling you, like, I sat there, and to motivate, like, when I was planning this lecture, I sat there, and I tried to implement this without continuations for, like, 2 hours. I, like, sat there, and I thought for, like, a long time. And every other implementation I got was either equivalent to this or worse than this. Okay? So, like, very smart people have thought about it, and this is how we're going to solve it. Okay? And you're going to see why. But one reason for this lecture is that both regular expressions are useful, and we get to use CPS for real. This continuation looks a little bit different because it returns a bool. We're going to drop the requirement that our function needs to be CPS. CPS is an idea that benefits us when we need to, but we can drop it if it's not necessary. So we're not going to be super stringent about the CPS. We just have a continuation. Okay? And now we have this specification. Okay? The idea is that if I give you a regular expression, I give you a character list, we're going to do the same thing that we did at the beginning of lecture, which is that if I give you a list of characters, which is like, you know, this, okay, I take off things from the front of the list as befits me, okay, until eventually I want to, like, finish with the rest. What I mean by that is match R given S, but really CS, and the continuation should evaluate to true only if you can split your input into 2 halves, the prefix and the suffix. And the match thing should only succeed if the prefix is matched by R and the suffix is satisfied by K. That means that the prefix is in the language of the regular expression R, and the suffix succeeds with the continuation. Okay? This is, don't ask why this is. We're just going to do it, and then it's going to work out really well. Okay, I really can't motivate this to you other than telling you this is what it does. And to give you kind of a picture again, oops, sorry. The picture is on the next slide. The point is that we split it up, okay? And basically, what I want to tell you is that this continuation specifies a condition on all of the suffixes I might choose. The regular expression denotes all of the possible prefixes I might choose. We want to strike a balance where the prefix is matched by the regular expression and the continuation takes care of the rest. And we will the way we'll do it is we'll backtrack. We're just going to take stuff off the front until we find something matching this and then hope that it satisfies our continuation. So for instance, if I had match RCs and I had this lambda, which specifies that the length of this suffix must be 3, this means that I would enforce a condition that all possible suffixes you might choose, the only ones that succeed are the ones of length 3, okay? Which is precisely this suffix, actually, okay? That is one way we might use this. So it's kind of an idea of if I give a different continuation, I get slightly different behavior. Okay? And we're going to skip over that. Here's the picture. Okay? If I have my entire character list C's, I'm looking for a way to push this boundary such that the prefix is still matched by R, the prefix must be matched by R, but the suffix, everything I didn't choose, must satisfy K. And because K is an arbitrary function, we have no idea what that looks like. The only thing we can do is use the function K and then see if it succeeds or not. Okay? But that's the picture, is that we're pushing this boundary forward. Okay? We're trying to push it to the limit. All right? Does this picture make sense to people? All right? We're going to see the implementation in a second too. And I will implement it for you. And then we may not have time for the proof, but that's okay. All right. And actually, I should have written this out, but whatever. This is what our code's going to look like. Okay? 6 cases. 6 cases. 3 slides, maybe. All right? So let's do it. If I'm going with this prefix notation, I want a prefix that satisfies R, right? So let's case on just our regular expression to see what prefixes match this. So remind me again, what strings are in the regular expression of 0? None. So that means there are literally no prefixes I can pick. So that means that what I'm going to do is I'm going to say false. I can literally never satisfy my regular expression with this. It doesn't matter what my suffix is. There are no prefixes. I don't get to move. Okay? So false, always. Okay? And then we're going to see 1. What's the string in the language of 1? Empty string. That means that my suffix must be the entirety of this string, right? That means my prefix must be the empty string. So if my suffix is everything, and my prefix is, it's kind of vacuous over here, the only thing I can do is check that my suffix condition is true. I must have that this suffix, whatever suffix I choose, satisfies k. So this is true if and only if C's, that is the entire suffix, the entire character list, is or satisfies this k. Does that make sense to everyone? Yeah. Okay. So I'm just checking that this one suffix I can choose satisfies k. Cool? All right. The next case I have is car. And this is the case where we actually start to make moves. Okay? Because what's the one string in the language of C? It's C, right? So that means that the only prefix I can ever choose is this if it's C, if it's that character. If it's not, I have no prefixes. That means I can't do anything, right? So here's what we're going to do. I need a case on my car list because I don't know whether or not it's going to satisfy. I have two cases. Either it's nil or it's cons, right? Or it's C prime cons C's. Okay. Well, if my thing is empty, if this is empty, I cannot take a prefix. There are no prefixes because it's empty, right? There are no characters. I want there to be a C on top of this. So what I'm going to do is I'm going to say false, right? Car C represents I'm trying to take a C off of the front, but I can't take anything. So this is unsatisfiable. I'm at the end, okay? End of the line. But if this C prime is the same as that C, then I want to take it off. Yeah? Let's move forward, actually. So if C is equal, actually, sorry. It's more brief to say this. I want it both to be the case that C prime is equal to C. And then what do I do from there? Well, I have taken my prefix. My prefix is just this guy. And I need to make sure that my suffix is again satisfied by k. So I just give the rest of it to k. Let's write on this line. K C is prime. Okay, this one's kind of confusing. Any questions on this? Yeah. This is not CPS, like full CPS. We're eliding that. It has a continuation, which helps, but we're not going to say it has to be CPS. This CPS serves us when we need it to. Okay. Any questions on this? The entire point of this is I take a C off if I can find it. Okay. If I can't find it, right? If this is not true, this whole thing is false. Right. If I can't take a C off, no bueno, donezo. Right. I cannot make progress. Otherwise, but also I need to make sure the suffix is true. Okay. I'm taking care of two things: prefix and suffix. That is all we're doing, okay? Otherwise, R1, R2. If I have the plus case, here's what I want to say. I want to say I find a prefix that is matched by either R1 or R2. And the suffix can be whatever as long as it satisfies K. I'm going to tell you that right now, the way I do it is just this. And we'll talk about it in a second. I OR both of them together. If I find one with R1, cool, scot-free, I'm done. But if this fails, then I'll try it with R2. Why not? These are basically, remember the recursive leap of faith. Our precondition is this will find us a match if it can find a prefix matching R1 that satisfies K. Or if we can find a prefix satisfying R2 such that the suffix satisfies K. Is it not the case that if I can find a suffix or a prefix for either R1 or R2, that's definitionally what plus of R1 and R2 needs to do, right? So if I can produce a match for R1 or R2, I don't care. Plus just says, give me either. Sounds good, okay? So that's why this is the right thing to do here. Okay, I just or else their conditions together. And I can use the result because this is not quite CPS, okay? Any questions on this? All right. The times case is a little more involved. Here's the idea. The idea is I want to find a prefix here which satisfies R1. And then my suffix should then satisfy this condition, which means that the suffix should itself be able to find its own prefix that is satisfied by R2. And then finally, this suffix is satisfied by K. Okay, I do two matches, right? Doesn't that make sense? If I have R1, R2, I take off a string for R, and then a string for R2. And then I continue with my continuation. Okay? So what we're going to do is we're going to make use of that continuation that we packed along for the ride. And I'm going to actually give you the picture so you can look at it while I'm drawing this out. Okay? But this is the idea. Okay? Matched by R1, and this is expanding. But this one also is expanding, matched by R2. And then we get the suffix to suffix, which needs to satisfy K. So the implementation is going to look like this. I want to first find a match for R1 on C's. And if I do, I continue with C's prime, which is this entire thing. That's C's prime after I find this thing. Then of C's prime, I want to find a prefix for it matching R2, okay? Such that, well, just that actually. Such that given this K, I satisfy whatever's left. Okay? So it's like I'm taking two big bites. I take a big bite for R1, and then I take whatever's left, I take a big bite out of that for R2. And then by my recursive call, by my recursive leap of faith, whatever's left needs to satisfy K. Does that make sense to everyone? Again, if you don't see like how this code works in your head by like stepping it through, that's okay. Think about it in terms of recursive leap of faith, like big picture what the code should be doing. I just take something out for R1, and then whatever's left, I take something out for R2. If you can understand the high level, you can convince yourself why it works. Okay? Any questions on this? Because this is complicated. Okay. And the star case is also a little complicated, but here's the idea. If I want to match a string list or a character list for star R, I can match with 0 or 1 times of R for my prefix. This means R, 0, or 1 or more. Well, how can I do that? That means that either it's empty, or if I take off R, I can keep using star R, right? Basically, what I'm going to do is I'm going to take off R, and then I'm going to say, OK, well, I could still take more R's off. So let me do star R again. Okay, so I take a bite of R, and I continue with star R. So here's what the this thing looks like. Basically, the observation is that the language of R star is the same as the language of either empty, or I get 1 R, and then I get 0 or more R's again. Right? Because if you do the math, it adds up. Either I have nothing, or I take off 1 R, and then R 0 or more times. That's the same thing as R 0 or more times. So this will be the same as that implementation up there. So I say, either I succeed with the suffix right now, that's equivalent to the 1 case, right? Because I don't take anything. I take nothing, but my suffix is the whole thing. Or I take a bite of R off, I take off R, and then I succeed with star R again. Because then I can keep taking R's off. That will ensure that we do it 0 or more times. Does this make sense to everyone? Well, sadly, there's a bug in it. Because no, in intention it makes sense. It's almost correct. But this implementation actually loops forever sometimes. In general, you should be very scared of whenever you see anything that gives the same arguments to the function twice. Okay? In particular, we gave it star R again, which is the same. We didn't decompose it, which means that if I gave it star R and we're recursing on R, maybe we loop forever. In fact, this might loop forever. Why? Because what would be the really bad case? The really bad case would be if this was the same and this was the same. That is neither changed. Is it possible for my suffix to be the same as my entire character list? It's true because I showed you an example. It was 1. So if this were to be C's, that is if the regular expression R had the empty string in its language, this would loop forever because it would just call match star RC's, which would call match star RC's, which would so on and so forth. Okay? So this implementation loops forever because we haven't taken care of that case. So here's what we're going to do. Because the prefix might be empty, there's 2 things we can do, which I'm going to call weakening the, weakening the, what is it, preconditions? Yeah, weakening the specification or strengthening the implementation. And here's a particular example for what would loop forever. If we had match star 1 given the string of A, Well, we're doing a star where 1 has nothing in it. So we take off the empty string. Basically, like, what happens is that if we had match star 1, we take off the empty string and we get the same thing. And then we continue with star of 1 and this whole thing. And then we take off the empty string, which means we get the same thing. And then we continue with star 1 and we take off the empty string and we loop forever. Okay? That's the concrete example. And this is not super important, but the point is basically, by analogy, if I wanted to weaken the specification on fact, I can do one thing. You know how fact loops forever on negative inputs? I can fix it in 2 ways. One is I weaken the specification by saying, hey, if you give me a negative input, that's not allowed. You can't do that. So I say, precondition, negative inputs are not allowed. Or 2, I strengthen the implementation by making it give me an option if I get a negative result. Either I can forbid you from giving me bad inputs, or I can work your bad input into my implementation. By analogy, we're going to do something here that's the same thing. So for the regular expression matcher, here's what we're going to do. Either we can be like, you can't give me something like star 1. You can't give me a star where the empty string is in this. And that's actually perfectly legal to do. It would be a wimpy way of getting out, but you could do it. Like when you're implementing any function, you can always say, that bad input you wanted to give me, actually by precondition, I don't care about it. Don't worry about it. That's allowed. It's kind of a wimpy way of getting out of it. The next thing we can do is we can make sure in our implementation that the suffix that was chosen by R is never the same as the original list. The prefix was never empty. Okay? And here's what we're going to do. Okay, and I'm going to write it out for you and talk about what it's doing as I write it. The modification was simply, I write K sees is true, which is to say that we pick the empty prefix, or here's what happens. I can write, I write match of R. So I take R off, and then when I get my C's prime, I want to make sure that this C's prime is different than that C's. Because if it's the same, I looped forever. I took a prefix that was empty, and then I might loop forever. So I want to make sure that C's is not equal to C's prime. But also I want to continue with my thing, right? So also, I do match R2, C's prime K. Star R. Okay? So I've only added this. The only thing I'm doing is I'm doing the same thing where I say, if I want to match R 0 more times, either I match it 0 times, or I match it once and then match it 0 more times again. With the added provision, I can't have taken nothing off. So I don't loop forever. And this will be the same thing where it will work. It will perfectly well match this language that I want to, but it's going to not loop forever now. So we lose nothing for this. This is what I call strengthening the implementation. Okay? That is the entire implementation. It's a lot, but also it's not. Because it kind of just relies on your intuition on what this is doing at the end of the day. I wanted to, so that's the entire implementation. Counted up, I don't know. We wanted to not give this continuation, right? We wanted to accept the whole string. And it turns out that we can write this function accept that accepts the whole string really easily. Because we just have the continuation be this function called list.null, which checks for whether or not a list is empty. That's what list.null does. It takes a nil and returns true and returns false and everything else. And do you believe me that if our regular expression matches the entire prefix and the suffix is empty, then our regular expression must have matched the entire string. Okay? That is all that's happening here. That's the accept function. Okay? This is really scary, but also it's kind of just relying on your ability to trust the fact that this prefix and suffix thing is doing what it says. I realized like when I was writing this function, I only talked about prefixes and suffixes with you. I didn't talk about like the code really, because that's what I wanted the high level to be. If I think about my invariants, I can program with my invariants rather than programming with the code, if that makes sense. I want to program by thinking about the high level, because if I get lost in this, if you think about the pure symbols that are going on here, you're going to get confused. Okay? And if you focus too much hard on what it's saying rather than what it's doing, you're going to get lost. Okay, so that's another application of this. There's a proof. We're not going to have time to get to the proof, but I'm going to talk you through it. Okay, and we do have a few minutes. So the point is basically we want to prove that match is correct, and I know I have to move on from this. Okay, it's a doozy of a lecture. Basically, what I want you to think about is this, okay? How do I assure myself that this match function actually works? I want to be sure that if match RC's k ever gives me true, it must be the case that I had to be able to split it into a prefix and suffix, such that the prefix was in the language of my regular expression, and k, that is the suffix given the continuation, or the continuation given the suffix, is true. I just want to be assured that that is true. And in fact, if you're dubious about whether or not this works, I can prove to you that it's correct. And we are going to be able to prove it, and this will be on your homework, by the way. So we're going to talk through this, and I need you on your own time to look through these slides, because we're not going to have time to discuss it next lecture. But if you are having trouble doing this proof on the homework, literally just look at this and then copy and paste, okay? All right? Not exactly. Not exactly. But copy paste your understanding, okay? I'm trying to stress to you this is important, okay? All right, so we're going to prove the plus case, and I'm going to talk through it to you, okay? Really high level. We're going to go breakneck speed, because I don't have a whole lot of time. But here's the idea. I want to prove that match RC's k is true if and only if I can split it into these parts. We're going to call this the pact, okay? I'm going to stop saying it out loud, okay? The pact is that I need to split it into a prefix and suffix, such that the prefix satisfies the regular expression, and the suffix satisfies the continuation. That's the pact, okay? How do we prove an if and only if? We prove it twice. We go once this way and once that way. We call that soundness and completeness. Going from right to left, that is right to left here will be called soundness. Left to right will be called completeness. Doesn't matter, okay? Let's do the soundness proof for only the plus case, okay? Here's the idea. And I've nicely colored it here so that hopefully you can follow along. I want to show that, actually the left to right was the soundness. I want to show that if I get true, then I must have been able to fulfill the pact, okay? So first, to prove it, we're going to assume the antecedent. We're going to assume that I could get true from plus, right? And then assume as your IH that we could get that soundness was true for R1 and R2, okay? In particular, if I look at my IH for R1, that is P of R1, it says this. If I could get true for matching R1, then I must be able to fulfill the pact on R1, okay? That means that I could find a suffix that was true, and I could find a prefix that satisfied R1, okay? And let's step through this. If I have true, I know that match of plus is true. Why? Because I assumed it up here. So this is essentially equivalent. That's our assumption, the blue assumption. But I also know that this, by our code, by here, is equivalent to match R1C's k, or else match R2C's k. Isn't that true? By definition. But by definition of or else, it must mean one of these is true. Without loss of generality, which means I don't care about the other case, let's assume that this one is true. If this is true, then we can use this guy, because these two are red. Both of these are red, meaning that I can use this if and obtain this. Okay? And if I can obtain this, then I have that by definition of the language of plus. If I have a prefix in the language of R1, I have a prefix in the language of the plus, because it's in either. Okay? And then, so if P is in L of R1, it's in L of plus R1, R2. And then if I have that P, the prefix satisfies plus, and the suffix satisfies the suffix, or the continuation, that's the theorem. Okay? Real fast, okay? It's okay if you don't get it. And then real fast, we're going to do completeness as well. All right? We want to do the reverse direction. If I have the pact, then I get true for match. Assume that the pact is true. Then assume that the pact is true for your R1 and R2, the IHs. Okay? If I have the pact for R1, that is, I have the IH on R1, then I must have that this implication holds. Okay? If I have this yellow assumption here, which is that P is in the language of plus and R1, R2, by the definition of languages, that means the prefix must be in either of these languages. It must be in R1 or R2 to be in the plus. We'll log again, assuming that it's in R1. Then if I have this purple thing, I can feed the purple thing in here, and this green thing I already have, and I get this red thing. Okay? So then I have that match must be true for R1. But again, by definition, match of plus is match of the or else of R1 and R2. And because I just got this, match of R1 must be true, therefore the or else is true. Therefore match of this whole thing plus is true. Okay. That is just me talking you through it. Please look this over on your own time. I'll probably record something and then or come to my office hours. That's it for the lecture. I know it was a lot, okay, but that's kind of how it is sometimes. Done.